No.
No? Okay.
Yes.
How low can
Yes?
you go?
Okay, so I can, okay. I have
No,
a
no,
line here.
bit you can go bit to the right. Yes, more or less.
Okay. I will try to stay in the frame.
Perfect. So, it's my pleasure to introduce to you Lars Kotthoff. He is a professor at the University of Wyoming. Before, he was a PhD student in Scotland, right? And then a postdoc actually in Ireland, then a postdoc in Canada, and then finally he became a professor in the States. We know each other for now, what, 10 years roughly, I think?
Oh, probably.
I say 10 years. So.
Yeah.
We were
both much smaller then.
yeah. Back then I was like that. And he's now a guest for the next 3 days here, and he will talk today about AI for material science, where he combines awesome technologies, what we were working on with spatial optimization, but also now applying to complete different kind of fields where I don't have much of any kind of expertise. And I'm really looking forward to listening to your great talk now.
Thank you for the introduction. So, this is part of the AutoML lecture, right? So this is kind of a different perspective on this, where we're using the same kind of things that we're using in AutoML, in particular Spatial Optimization, for something in a completely different domain. So that might be interesting, or maybe not. And I have actual physical things to show, so that should be exciting. We have quite a bit of time for this, so if there's any questions at any point, feel free to interrupt me, and I will try to go into some details on some of the more technical things. If I start to be boring, let me know, and then I can speed ahead and talk about something else as well. So, let's try to make this interactive.
Please let me warn you, we'll be recording that and it will be put on YouTube later on.
And of course, every time one of you will talk, the camera will turn around and be directly in front of your face. So don't worry about anything at all. Okay, so before I get started on the actual talk, I want to show you what this actually looks like. Let's see if this is working. Yeah? Okay, so here we have our fully automated laser setup. So we have AI to control lasers. We're still working on the sharks. But we don't, it's Wyoming, we don't have any sea creatures. Anyway, so here we have our fully automated setup where our spatial optimization in this case controls a laser to repeatedly pattern a particular sample of precursor material and evaluates the results, feeds that back into the spatial optimization process, and then proposes the next parameter setting based on that. So you can kind of see this a little bit here, and I'm going to pass these samples here around where you can see what they actually look like. So these spots that you see on there is the result of the laser patterning this material. Why are we doing this? Well, because AI and lasers are cool, but also because we really want to produce, we want to produce graphene from a precursor material. So graphene is this wonder material that has been discovered quite some time ago, but nobody has really figured out what actually to do with it yet. And part of this is because it's actually quite difficult to produce in practice, at least at scale, and this is what we're trying to address here. So the idea is that we have some precursor material, and in the sample that's going around, you've got 2 different precursor materials, and we will see results for another one later. By irradiating that with a laser, we can turn the irradiated part of the material into graphene from the precursor material. In particular, that means that we can take something that is not an electric conductor and then irradiate it, create graphene, which is an electric conductor, so we can create circuits on really any kind of carrier material. So think flexible electronics and little sensors and stuff like that. One of our partners on this, one of our sponsors on this is NASA. We're interested in this for in-space manufacturing, because you can essentially do this with the equivalent of a laser pointer in some cases. So you don't need a lot of machinery that you need to bring up into space to be able to do this. And various precursor materials of graphene apparently just float around in space. So you literally take up a laser pointer, and then instead of, when your electronic component breaks, instead of hoping that you have it in the stuff that you brought from Earth at exorbitant cost, you can just manufacture it right there. So really very interesting application. We're not quite there yet, so we're not quite manufacturing electronic components yet, but this is essentially some of the precursor studies that we've been doing here. Okay, so I think I've said most of this already. Yeah, so the crucial point, and the reason that we're applying techniques that you would also apply in AutoML is because we need to tune these experimental parameters very carefully to achieve good results. So that there's the obvious things, right? If the laser you apply has too much power, you burn a hole into the material, and that is clearly not desirable. Similarly, if you don't have enough power, then nothing happens, so that's also not particularly desirable. And also we are very much limited in terms of the number of evaluations that you can do. So you've seen the sample go around, so it's a really small thing where we can only do a very limited number of spots, and producing this, so just producing the precursor material apparently takes weeks, which for me as a computer scientist is like, what? How long? So we can't just run lots of experiments just for the fun of it, as we usually do as computer scientists, because hey, it just runs on the computer. We can run as much stuff as we like, right? So here, this is really, the evaluations are extremely expensive, and we want to really use these as best as we possibly can, because there's all kinds of issues involved when we start talking about actual physical experiments that you need to produce material for, and that you need a relatively expensive laser setup for. So here's another picture of that, and that needs to be put together by a skilled operator and then operated, etc., etc. Yes?
So now you said a minute ago that you'd like to use it in space because it's so easy to do there.
Yes.
Now you're saying it takes weeks and it's super complicated.
For the process that we're currently using. And
Okay.
there's different ways to get to the precursor material. Okay, so this is where I have to give you a little bit of background. We are essentially producing at least some of these precursor materials from coal, because at the University of Wyoming, where I'm at, are we recording this? So we are let's just say that we are a natural resources state. There's a lot of coal production in the state, and a lot of people are very keen on finding uses for coal. So yeah, that's why we're doing this. Except, of course, we need tiny amounts and not like railroad wagons full of coal. I mean, but yeah, so there's different ways of getting the precursor material. And that's why I'm saying we're not quite there yet. So this is only part of the process. But the idea is really that the stuff that we've been doing here, you could then apply it in space to do a similar parameter optimization there for the environment there, which is very different from what you have on Earth and in our lab. But you don't need to, do manual experimentation or the other things that you might do for parameter tuning. Yeah.
I just wanted to ask the experiment. How sequential is it? Do you have multiple steps included in there, and do you simply parameterize them irrespective of their sequential nature, or?
So at the moment, the evaluations are very sequential. So there exists one of these setups here.
I do not mean
Yes.
the evaluation, but rather the procedure itself. Is it kind of a multi-step procedure?
I'll get to that at the end, actually. To start with, yes, it is entirely sequential. And this is really because for the particular sample that was going around, we radiate the spot and we can immediately measure the result. So that is what you saw in the previous video, because we can use the same laser with a much lower power to evaluate. Actually, my next slide here. So how do we do this? It's kind of an optical blown up image that you see at the top there of one of these irradiated lines. And the way we measure this, there's two ways really. The cheap way to measure this, which we can do with the same laser, is to do Raman spectroscopy. And in these we have these two characteristic peaks, before and after. So as you see, the relative intensity of these peaks changes very dramatically. So if we measure essentially the ratio of the area under these peaks as our optimization criteria. Depending on which way you set it up, you can either maximize or minimize, so it doesn't really matter. I think the experiments we did, we minimized, no, wait, we maximized. We keep changing it sometimes, depending on how the students feel at that particular, on that particular day. The other way to measure this, and what we're really interested in, is resistance. So we want to be able to create conductive lines. That turns out to be much more difficult from a technical perspective because we can't do that with the laser. So that involves taking the sample out of this machinery that you saw before and putting silver ink pads at the end of the lines that we drew, and then measuring the resistance there. So this needs to go into a separate piece of machinery. After that, we can't easily put it back because of alignment issues and stuff like that. And then we're actually doing batch optimization for vision optimization. So I will get to that at the very end. So these are results that are like 3 weeks old or something like that. Maybe not quite. Maybe like a month. So relatively recent results. But there was a gap of, I think, more than a year between these initial results and the samples that you saw going around, and then us being able to do this for lines because of COVID, but also because of all the technical difficulties involved in the experimental setup. So this is, and again, this is, sorry, I will step into the camera. This is one of the things where this collaboration has been really eye-opening for me. Like, well, that sounds really easy. Can we do that like tomorrow? And a year later, yes, we can do that now. Okay, great. Anyway, also, I should say, as you saw on the first slide, I'm mostly talking about the work of other people here. I'm just taking the credit for it. So this was really a team effort between chemical engineering and computer science, mostly on the chemical engineering side because they did all the actual physical stuff, so building the experimental setup and then operating it and wiring up all the machines and stuff like that. Okay, so what parameters are we actually, excuse me, what parameters are we actually dealing with here? So there's a laser power, kind of obvious, right? So you can vary that. The duration for irradiating a spot, or in the second scenario where we want to do lines, the speed at which we move the laser, although it's not quite that easy in practice, so if you just move it at a constant speed you don't get the same kind of transformation of the material in every place. Then we can also control the pressure in the reaction chamber, and the final thing we can control is the gas in the reaction chamber. So we have three categorical choices essentially, so we don't have any relationships between the gas, at least as this model is concerned. I've put that into parentheses here because we ran quite a number of experiments, and it turns out that really you always want to use one particular gas. The results you get with the other gases are so clearly worse that it's not even worth investigating this further, in particular keeping in mind that we have this precursor material that is extremely expensive to create. So we're talking about a really quite small parameter space here, especially by AutoML standards, right? I mean, okay, 3 parameters, okay. It's just about large enough that you don't want to do this by hand, but really where the difficulty comes in, as I mentioned before, is that we are severely limited in the number of evaluations. So we can't just do 100 or something, and it's more like a dozen, and we've been able to get good results even with small numbers of evaluations. Okay, so this is where I might be talking about things that you already know. I don't know whether Marius talked about, yeah, you're okay, let me skip all of it. Oh, okay.
No.
So, slight diversion, automated parameter tuning, which you are familiar with, or hyperparameter tuning, depending on. Here we call them parameters because these are the parameters of the process, and then in machine learning you obviously call them hyperparameters because there's also the parameters of the machine learning model, which we learn. But in general, the setup here is that we have some process that we don't really understand. That could be some complex machine learning system, or that could be a laser that we're shooting at some material to transform it into graphene. We don't know anything about it. We want to treat it as a black box, but we have these knobs that we can turn essentially, and we want to find the best setting for these. So particularly here, we don't need the first principles understanding of this process of converting whatever precursor material into graphene. And while we do have that to some extent, it's not good enough that we can essentially just predict this, that we can just take our physical equations and say, oh yeah, if I solve for laser power here, I get 100 milliwatts, so that's the optimal value. It doesn't work like that, at least not so far, unfortunately. So we have to treat this exactly like you would treat an automated machine learning system or any other system that you might want to choose. Yes, so we evaluate different parameter settings and see how that affects performance, and then we try to relate the different parameter settings to the performance that we have observed. And as you know, these are mature techniques used in many areas of AI and machine learning and elsewhere. And in particular, Spatial Optimization has a long tradition in engineering applications because, I mean, even like 100 years ago, if you want to build an airplane, you don't do that by building a candidate airplane and then finding that, oh, this didn't work. Let's try something completely different, build a complete airplane and then try that again. But you do that in a more intelligent fashion. So, you have some knowledge about the different parts and you have some first principles knowledge that you can inject into that. So, same kind of idea, very roughly, very high level here as well. Okay, you've probably also seen this figure here. Do you show this figure in your slides? Yes? Okay, good. Who can explain this figure to me? All of you. This is where it turns interactive. Yes? I've got time. I'm here until Friday. Yeah?
If you have multiple parameters of different importance to the result, then with random search you test more spots for either parameter, so you're more likely to get a good result with random search.
Right. And in particular, you don't want to do something like grid search where you're just blindly testing everything because you might be wasting a lot of evaluations, right? So, but yes, I mean, if you try random search, which I guess they have maybe, then you will know that this is surprisingly competitive in many cases. Really, main point here is we don't want to do grid search because we might be wasting a lot of evaluations. So extremely expensive, and yeah, okay, I mean, if you can afford it, then you'll find the optimal result, but in practice, we can rarely afford this. Certainly not in this particular case.
But if you would like to learn something about your landscape, right, then a more controlled study like grid search is nice. So
if you want to learn something about your landscape, yes, absolutely. And again, if you can afford the evaluations, then yes. And so we've actually done this for the analysis of the surrogate models, because these are then cheap to evaluate, right? So there you can do something like, well, not grid search, but grid evaluation, and try to learn something. And we unfortunately, we didn't really learn anything. But that was almost certainly because the surrogate model was built with such a small number of data points that it's essentially, yeah, okay, in certain areas there's good data, in other areas we know nothing. So.
But nevertheless, I would like to ask, or maybe that's coming later, but here's the assumption that there's at least one of your dimension unimportant, right?
Yeah.
So is one of your 3 dimensions then unimportant? As we only have 3, right?
So the fourth one here, so the gas in the reaction chamber, actually turned out to be unimportant.
Okay.
Unimportant in the sense that as long as you have the right value, it doesn't really matter. So that there's one obvious value that you want to prefer. And let me see, for the other ones, so there are relationships between the first two, right? Because essentially it's about the amount of energy that you put into the material, and you control that by both the laser power and the duration for irradiating the spot. So a grid search in this case also would have led to essentially a lot of wasted evaluations where we already know that, yeah, okay, with this duration, with this power, didn't do anything. So giving it a slightly lower power is definitely not going to do anything. Similarly, if you're burning spots, if you're burning holes into the material, and then we do the same thing but for a longer time, that's also not going to work, right? So.
but then even with random search, you are not very lucky to figure that out.
Right.
It seems like a fairly linear relationship.
That's why we didn't do random search.
Ah, awesome.
So this is what was that your question?
I wanted to ask, the gas is categorical, so random search wouldn't necessarily get every gas once in the same amount of tests?
Well, it's really only 3 choices. So, but yeah, depending on the number of tests, we might not get everything. But yeah, I mean, so just to emphasize this, we use neither grid search nor random search. We use spatial optimization. I just want to set the stage. I wasn't entirely sure what what Marius has told you so far. So I just wanted to, you know. Okay, so we have spatial optimization, which you've also covered, right? So some of this is going to be redundant, or I could ask you, who can explain spatial optimization to me? That might go a little bit far. Anyway, so here's a very rough, high-level description of it. We take some initial data points, so this could be random evaluations, a small number, whatever the suitable definition of small number is in a particular context, and then we build a surrogate model of the parameter response surface, so parameter, here the parameters of the experiment and the ratio for the conversion that we measure. Then we use this model to choose where to evaluate next, so essentially we make a series of predictions and we, for example, choose the one that would improve most over what we have seen so far. We evaluate that, that gives us a real, true data point. We train the next iteration of the model or update our model, and then we repeat that until we run out of space of these tiny samples that you saw earlier. And intuitively, this is much like you would do it as a human, right? You start a bunch of initial evaluations just to get a feeling for what the parameters do, and then you're like, oh, hang on, okay, parameter 5 here. If I increase that, I see better results, so let me try doing that. And then you do that and you observe results and you adjust your beliefs, etc., etc. In particular, it allows a much more targeted exploration of the new configurations and optimizing the value that we're interested in than either random search or grid search, because these are completely non-adaptive, right? So you design your experiments and then you run them and you're done. And here we have this iterative process where we actually take the things that we observe into account and decide what to do next based on that. Okay, so here's a picture that summarizes this, but you've covered this in class, right? So you're all very familiar with this, yes? Who's not familiar with this? Marius, can you leave the room just for a second?
Sure.
No, okay, so here are how the different pieces work together, right? So you have a process that we want to optimize. In our case, this is the actual physical experiment of taking the precursor material, shooting a laser at it, and then measuring the result. Or this could be an AutoML system that is training some kind of model to predict, I don't know, house prices or something like that, and is evaluated. Lots of parameters. It might look like this. Then we have we evaluate our expensive process here. We record the result of these evaluations. We use that to train our surrogate model. This could be, I mean, common choices are random forest and Gaussian processes. I think in our experiments we mostly use Gaussian processes. Then you evaluate on these surrogate models. So as the name suggests, you are replacing, in a sense, the underlying process, where now to find the optimal value to get the optimal accuracy for your model, or the optimal conversion of precursor material into graphene, you're simulating, in quotes, that by asking the surrogate model, hey, what do you think this would give me as a result? Hey, what do you think this would give me as a result? And you can do that many, many times per second, extremely cheap, right? Evaluating a machine learning model. And that then gives you an idea of, okay, this is what the surrogate model thinks. This is maybe where I should evaluate next, because it thinks that here I would find some good results. So that's what we're going to do. We're going to evaluate at that point, and depending on the results, so either that was, yeah, okay, that was pretty good, or, oh, actually that was completely off. We update our surrogate model, we feed it more data at each iteration, another data point, and then we do the same thing again. Okay, does that make sense? And we will, I have some example iterations in a couple of slides here. So in this context in particular, really what we're trading off is essentially speed and accuracy. Coming back to our multi-fidelity discussion from earlier on, because at one end of the spectrum, this end, we have running the actual experiment, which is not very fast at all, right? So that this takes time to prepare it, to actually run it, to evaluate it. You need somebody who's not going to blow up the building or set it on fire which is why they don't let me do these things. But we get really accurate results, assuming that, of course, we can measure everything accurately and I don't mess something up along the way, right? Then this is the gold standard. This will give us the ground truth values. Other end of the spectrum, we have some AI model, so some surrogate model, for example, which we can evaluate really, really cheaply. We can evaluate this thousands of times per second easily, right? But is it going to be accurate? Well, clearly not as accurate as actually doing the experiment. So there's a trade-off here, and somewhere in the middle, as an example here, I put a numerical simulation because in many cases we can do that as well. And then we have essentially this hierarchy of evaluation methods. So we can say that, well, we want to run the actual experiment, and this is going to cost us a lot, or we're going to run the simulation, which will be cheaper, but is also, in a sense, an approximation, so it won't give us exactly the ground truth value, or we're going to evaluate our surrogate model, which is really, really cheap, but yeah, the quality of that is not going to be that great in many cases. Yes?
So at the moment BO is now proposing a new configuration. Is then an expert checking whether that really makes sense or could blow up the building?
Well, so that in this particular case, that's essentially how we define the parameters, the parameter space. So we have set this in a way, in particular for the pressure of the reaction chamber, that we can't blow up the building.
Okay.
At least that's what my colleagues told me. And as far as I know, they haven't blown up any buildings yet. So,
But
yeah,
that
I guess
means
it
you need a
works.
lot of expert knowledge actually to design the space then.
Well, to some extent, yes, but in our case, this is really essentially determined by the safe operating limits of the machinery. So we have the reaction chamber, and that is safe up to 100 psi or something like that. So, and of course, we're not going to set it higher than that. What does actually happen in some cases is that we are literally just burning through the material. And that's fine. I mean, this is set up in a way that it will not set the rest of the building on fire. And yeah, that is obviously a bad result, and that we can take into account in the optimization, but it doesn't blow anything up or set anything on fire.
Will you talk about how you will consider that in the optimization?
We didn't really consider that. Essentially what happens is that you get a really bad result. So it
Yeah, but for a surrogate model, it really matters actually how bad it is, right? So if it's then set to, I don't know,
Yes.
the 1,000 or a million or whatnot, can really mess up your surrogate model, unfortunately.
Right, and fortunately in our case that kind of happens automatically because we have this continuum of what is the relative area under these peaks here. And in some cases you have no peak, right? So, and then you might say, well, 0 as the worst possible value, or depending on which way you're doing this, some really large value. So this kind of comes out automatically. There's more technical issues because in some cases, if the material is really badly damaged, then we don't even get anything like this. So we can't even really quantify this. And this led to some revisions of the parameter space over time. In particular because we also observed that, for example, for really high power, we don't really get that great results anyway. So there was an evolution of the parameter space happening over time here as well.
Is the expert needed for that, or could one automate that process actually?
That's a good question. I mean, in principle, you could certainly, well, no, you do actually need human intervention in this case because you need the human to realize that this evaluation that gave me a nonsensical value for the ratio here is something that shouldn't have happened. This is a value that doesn't make sense here.
An expert should know that beforehand, right? It should,
Well,
can be defined actually what is the reasonable range of Y values you can observe, no?
Well, a real expert should not need to do this optimization. They should just know what the optimal values are, right?
No, I would disagree with that because that's going to really depend then on your environment, whether you're in space, on Earth, or what kind.
Yes, and it's the same thing here.
Okay.
So it does depend on the precursor material, and no two batches of the precursor material are exactly the same. So of course, I mean, you get some values that are just, if you're going to irradiate this at 5 watts for a minute, yeah, okay, you're going to burn through it. It doesn't matter.
Okay.
Unless you have like, actual coal brick or something, which might catch fire, so that's also bad. Anyway, so there are some parameter values that are clearly, they're not going to do it. But then you kind of have, as with hard AI problems, you have this phase transition, right? So you have the set of parameter values that are clearly safe. They might not work, they might not give you the desired result, but they're not going to do anything bad. You have the set of parameter values that are clearly unsafe. You don't want to do this because it's outside the operating limits of the machinery, or because you can, looking at this, immediately see, yeah, this is just going to burn a hole in the material. And somewhere in between, you have the parameter settings where you're not quite sure. Is this going to be fine? You just have to try it. So, and that's essentially what's happening.
Is it actually a very noisy process? So can it be that sometimes it's burning a hole and sometimes it's working? Or is that so fine controlled that everything should more or less turn out if they calculate
it is somewhat noisy. We are still actually working on exactly quantifying how noisy it is. So for the experiments that I'm going to show you, at least for part of these, what we did is run everything 3 times, measure everything 3 times, and then I think we got the average across those. But the variation between those 3 measurements, if you do the same thing 3 times, was essentially small enough that the improvements that we saw, we can be sure that those are real. That said, there is some variation, and we are also at the moment only doing this for individual batches, because across batches there's variation as well. So, and we can't even really quantify this at the moment. There are, when we come to the resistance measurements, there are variations there in terms of how exactly is everything aligned, and where exactly do you put the probes that measure resistance. And so we also do that multiple times and then average across that. There are many sources of noise in there, and unfortunately, because of the small number of evaluations, we can't really even evaluate conclusively, at least not as much as I would like, where noise might come from, because we essentially can't avoid it. But yeah, so there are sources of noise, but we made, I would say, a reasonable effort to make sure that the improvements that we saw were actually real and not just caused by noise. Okay, let me go back to, where was I? Yes, okay, cool. So we kind of have this not quite continuum, but we have this trade-off between speed and accuracy here. And this is one of the things that we want to have a look at going forward. So our colleagues in chemical engineering are now working on this middle part, a simulation of this process, or at least parts of this process. And then the question essentially becomes, if we want to put that into the context of spatial optimization, not only where do we want to evaluate in the parameter space, but also what type of evaluation do we want? Can we get away with a cheaper one, or do we actually need to run an experiment? And obviously, if we can do that efficiently and effectively, then we could improve the results by quite a lot by essentially interspersing a few expensive real evaluations with lots of cheaper simulations that would in the end then hopefully give us about as much information as if we had run a much larger number of experiments. Okay, so then let me show an example for Bayesian optimization here, and you might have seen something very similar to this already, so just as a refresher, top panel, okay, you can't really see the gray. Anyway, top panel, solid line is a function we want to optimize, so that this is the underlying ground truth function, which in the usual setup for Bayesian optimization we do not know. This is the black box, so this is our graphene optimization process, or this might be your AutoML system. Here, for the sake of being able to show you, I've actually defined this, so there's kind of this quadratic function overlaid with a sine or cosine or something like that. So we want to find the lowest point in that, so we want to minimize our value here. Then we have a bunch of initial values that we've evaluated, so these are the red points here, and these are just kind of, spread out across the one-dimensional parameter space in this case. To that we have fit our surrogate model, the dashed line, and we've also well, we've chosen some type of surrogate model like a Gaussian process that allows us to quantify the uncertainty of a prediction, and this is the gray shaded area that you can see there. In particular, at the points where we have evaluated the process, the uncertainty becomes 0. We know the result. Of course, that's assuming that we have a non-noisy process, as we have in this toy example. And the further we get away from that, the larger our uncertainty becomes. Okay, so yeah, we kind of skipped over our optimum here, so we don't really know anything about this, denoted by the relatively large uncertainty there. But essentially, our surrogate model thinks that there's nothing really good there. Based on that, we can then compute our acquisition function in the bottom panel here. So this is expected improvement here. And essentially, the peaks coincide with spaces, with points in the parameter space where I expect to see an improvement over the best value that I have found so far. So that would be, well, we kind of have one here, and then we have one there, and we have one here. We don't really expect anything good there because, well, we have observed bad values there, right? And we have other evaluations reasonably close so that our uncertainty is not too large there. So this is a combination of the predicted value, so the dashed line that you see, and the uncertainty, so the gray shaded area. And that would also, again, kind of intuitively how you might do it as a human, as in, I don't expect anything good to be in that particular part of the parameter space, but I'm really unsure, so there could be something there, and that might be some motivation to actually do an evaluation there. Right, so, and that's what we're doing here. So here we're now going to propose the next point to evaluate. More challenges. The next point to evaluate as the point that coincides with the highest peak in our acquisition function, so that this is the blue triangle there. So then we do this, and we find that, yeah, okay, this was actually pretty close to what the surrogate model thought it was going to be. We add that as a round truth point into our surrogate model for the next iteration, so you can see that the uncertainty there collapses to 0, and we repeat the process. So now our highest expected improvement is on the other side of this point. So again, kind of intuitively how you might do it as a human. You look in the neighborhood of good points that you have observed. So we evaluate that, and we find that, well, it's actually worse than what we found before. Update our surrogate model, and now we essentially don't have anything in this part of the parameter space anymore. We have done a bunch of evaluations there. We have found nothing that's better than this initial red point that we see there. So what are we going to do now? Well, we're going to look in other parts of the parameter space. We could look over here, except that there we also have a bunch of evaluations, so, well, it doesn't look that great. Aha, what about this middle part? We don't know anything about it. Right? The surrogate model doesn't think it's going to be very good, but our uncertainty is also quite large. And if we take the lower bound of this gray shaded area here, then it could actually be something that's quite good. And of course, in this particular example, it turns out that now we've essentially hit the jackpot, right? We are very close to the global optimum here. Update our surrogate model. Again, you see that the uncertainty there collapses to 0, and the dashed line bends down to become closer to the solid line. Evaluate something very close to there, because now we have found an area of the parameter space where we do see much better performance, much better values than in other areas, so we want to keep exploring there, and we essentially continue doing that for a bunch more iterations until we've really discovered this optimal value there. But now the spatial optimization is essentially focusing on these particular parts. Until eventually the uncertainty for kind of these parts here becomes so large that it will explore there as well. So this is the usual trade-off between exploration and exploitation that I'm sure you've covered, right? So I will not go into that anymore. Just let me go briefly back and point out maybe one point here. The initial surrogate model that you see here is crap. it's not even close to the actual underlying function, right? And that's perfectly fine. As opposed to kind of the usual setup in machine learning where you want to get a model that is really very accurate in terms of the prediction it gives you of the underlying phenomenon that you're modeling, whatever that might be. Here we don't care as much, because on one hand we iteratively define this, so even if we start with something bad, like here, at the end we have something that is actually much better. And we also only care about parts of this space, in particular this part. We don't care about this end here, we don't care about that end there, and as you can see the model has not actually improved there. It's still pretty crap, but it doesn't need to be good, because all we need to know about those parts of the parameter space is that there are no good values there. How bad are they? Well, don't know, don't really care, right? I only want to know where I can find the good parameter values, and as long as... That's a lot of glass.
I think I need 2 more times.
Okay. As long as we have an accurate or reasonably accurate model of the good parts of the parameter space, we don't care about the rest. So kind of different setup fundamentally to the usual machine learning setup where oh sorry, I have to walk back into the camera. To the normal machine learning setup where we want to get good accuracy for everything, right? And in particular, you're aware of adversarial attacks and things like that, which essentially leverage that in certain parts of the space the model is not as good. Really bad when we talk about self-driving cars. Perfectly fine for Bayesian optimization, because as long as we're good in the relevant part of the parameter space, it doesn't really matter what's going on in the other part. Okay, so yes.
Can I ask something which bothers me actually for years now?
Mm-hmm.
You said everything is super expensive in your setup, right? You would
Yeah.
like to save actually function relations.
Mm-hmm.
If we're now looking here at the EI range, we see already after 7 iterations, EI becomes very, very small, right?
Right.
We could actually say that the model is now fairly confident. It shouldn't be. No, it's telling me. The model should be fairly confident there's nothing more we can gain here, right?
Right.
So, would you say we would now terminate the process and say we don't invest any more points, or would you say, nah, we don't know whether that's a good model fit at all, so we have to keep running, but
Yeah.
we don't know when to stop at all?
I would say the latter, because so we kind of have a weird setup with respect to the function evaluation or the cost of function evaluations, because they are extremely expensive. But once we have produced the material and we have put it into the laser thingy, we might as well run it until we have filled up all the points, right? There's no point in only doing part of the sample, because we can't use it for anything else. So, and that's essentially what we did. We said, well, we can afford 3 of these for an experimental campaign. So we will, and I don't remember how many dots that was exactly. It's something like 25 per sample, if I remember correctly. So our total experimental budget is something like 75 iterations, and it doesn't make any sense to stop at 60. That said, in practice, and okay, next slide, does this actually work? Yes, great, okay. In practice, we do find that we kind of plateau, as you can see here. Okay, so what am I showing you here? The bar plot on the left-hand side is just a summary of the initial random evaluations. I think it was 10, I'm not entirely sure. So just to give you the range that if we do this randomly, this is what we're going to get. Everything after that is Bayesian optimization. Okay, so what do we have? We have the plus, which is the predicted value. So this is what the circuit model said. This is the evaluation, this is the value you're going to get for this particular parameter configuration. And we have the circle, which is what it actually was. So in some cases pretty good, but in other cases, yeah, kind of far away. And the gray shaded area is again the uncertainty associated with those particular predictions. Main point here, as soon as we start the Bayesian optimization, we start to see better values on average than we saw in the initial random stuff. And then at some point we discover something much better. I mean, we kind of stay at that plateau, right, in terms of, so that this is maximizing the ratio. in terms of the values that we're observing. Box plot on this side here is a summary of all the values we got during the actual values we got during the Bayesian optimization. And particularly you can see that, well, there's a little bit of overlap between the two box plots, but not a lot, right? And certainly the median values are quite far away from each other. So we're certainly doing something better, and that this is also larger than the measurement uncertainty that we evaluated separately. Yes?
Would it really be of concern if your box plot on the right would not be better than on the left? Because one could construct actually landscape where I believe that Bayesian optimization has to explore quite a bit, discovers a lot of poorly performing configurations and so on, that the box plot maybe not looks nice.
Yeah.
And only from really rarely hitting good points, and then it's more as in your distribution of sample points and outliers.
Right. Yes, absolutely. Absolutely right. And we have also, I'm showing you just a selection of these results here. We have about a dozen or so campaigns overall, and in one or two of them, the random evaluation actually got really lucky and found the overall best point that was clearly better than anything that the Bayesian optimization found. So yeah, okay, it's random, right? So you can get lucky. But in general, for most of the campaigns, this was not the case. And it does kind of look like we're learning something as well, right? We have this step in here where we're clearly discovering something that improves results. So it seems like it's really that the Bayesian optimization is doing something well. I think I can confidently say that it is the Bayesian optimization that is actually learning something and learning to optimize, even with a relatively small number of data points here.
But looking at that curve actually, and I really like the dots and the pluses actually compared. It looks like the GP hasn't really learned the landscape, right? So even later iteration, that's still far off. And so if we could afford more iterations, it would be maybe nice to spend more, right?
Yeah, absolutely. I mean, we've explored a tiny part of this parameter space. I don't remember, but so if we take all possible parameter values, then we get something in the billions of parameters.
The three parameters.
For all the different configurations. So all the different value settings.
That's very fine-grained actually.
Yeah.
I see.
No, we can set power, for example, we can set at the millisecond level, and the range is something like I think 100 milliseconds to 5,000 milliseconds or something like that. So we have a large range of values. And okay, I mean, it's obviously not going to make a difference if we go from 334 to 335, but there is a large number of possible configurations, and this is what I don't 50. Thank you. Yes. So a tiny fraction of that. So we have learned something about the landscape, but we haven't learned the landscape at all.
Yes, but it has to be a very complex landscape actually, right? So normally I would expect that 10D, so 10 times 3 in your case, should actually cover your space fairly well with VO. And now you even spend at 50, not only 30, and you're still a bit off.
Well, so in some sense, the landscape is relatively well behaved because we have these obvious relationships between the parameter values. So, you know, like between power and time. As you increase one and decrease the other, you kind of get the same result. But then we have all the caveats of an actual physical evaluation, so it tends to be a little bit noisy. And we at least, I mean, so we did analyze the models and we found the obvious stuff. Like if your power is too high and your duration is too high, you're going to get bad results. So you want to have some kind of sweet spot there. And this is what the model discovered, but it didn't go beyond that. So it was kind of, you know, what we intuitively knew already, but it didn't, at least as far as we can tell, so far with the analysis that we've done, it didn't discover anything surprising, like, oh, you want to avoid these particular values or anything like that. And also the evaluations tend to be concentrated in certain parts, right? You find something good and you do a bunch of evaluations there. So we haven't really covered. I don't think I've plotted in this presentation, but we've plotted the points in our 3D space because we can actually do that. It's 3D, right? We can just about do that. And it's really that, you know, you've got a cluster of points here of evaluated points, or a cluster of evaluated points there. There's nothing in between. And then there's a point over there, and then there's a point over there. So we haven't really covered the landscape at all, which I would like to do. And this is when my colleagues tell me, but it takes weeks to produce this. So yeah, and then run an experiment just for the sake of, you know, your intellectual curiosity, as in, I know that this is not going to be good, but I want to do it anyway. It comes, yeah.
When you're saying it needs weeks to be reproduced, is it actually someone standing there in the lab and reproducing it by hand, or is it an automated process?
Well, it's a semi-automated process. It's essentially, they have to, there's several steps to this. They have to grind down the coal or whatever it is that they start with, and then make that into an ink using some kind of, no doubt, very expensive and dangerous chemicals. And then this ink is put into some special instrument, and this is then sprayed in thin layers, deposited in layers over this material, over the carrier material. And this has to be done several times, and I think it has to dry in between, or I'm not entirely sure what it involves. It's just a really laborious process. And it does involve a lot of human effort as well. So it's not just like an AutoML system. You push a button and you come back next week and you have the results. But it's like, okay, you push a button, then you check. You push a button again, then you push a different button, then you check again. So kind of like this.
It's a control system, a control problem, eventually.
Yeah.
Especially with the simulator.
Right.
Actually, one question regarding the parameters. Since they are physically motivated, obviously, and we kind of know a lot about lasers, at least physical people in the physics department and engineering department, and there are equations that kind of describe their behavior and their interaction. Is there a sensible way in your setup to inform the BO of set equations?
This is one of the things that we want to do in the future as well. In particular, this very simple relationship between power and duration, right? So that as you increase one and decrease the other. But the reason we haven't done this so far is because initially my colleagues in chemical engineering worked with the physicists on exactly this, so that they were trying to do this from first principles. And the physicists essentially told them, hey, look at this part of the parameter space. And it turns out that they were completely wrong. So the results that they got in that part of the parameter space were bad, and then as soon as we tried Spatial Optimization, which knows nothing about it, it went off to a completely different part and got much better results. So I guess a nice successful Spatial Optimization here, but really in the end it's just that this process, at least in practice, is really not well understood. And I'm not a physicist, right? So I don't know, I'm sure that the first principles understanding of lasers and stuff is there. It's just that in this particular context, in this particular reaction environment and irradiating this particular kind of material, you just can't do it. At least we can't. I'm not saying that nobody can do it, but at least
but maybe it's interesting, given that you have some data, that you kind of forward this data and let some physicists add in their model and check if the evaluations kind of still make sense given the knowledge that there is. And maybe again then kind of backloop into your model the information that you might have validated from that.
Right. So this is one of the other things we want to have a look at. But at the moment, the main thing that this suffers from is a lack of physicists, because the postdoc who was working on this has left, has taken a faculty position elsewhere. How dare they? And so, but also this is the really laborious process, right? Because now you need somebody who is really an expert in all of this to very deeply think about, okay, what does it mean that this data point is giving me these results here? We kind of tried to do a little bit of that, as I mentioned earlier, through analyzing what the surrogate model has learned, but as I said, we unfortunately, beyond the obvious stuff, we weren't able to recover anything. Now that doesn't mean that there's nothing in there. There could be some, if you look at this as a physicist, you're like, oh, okay, that's interesting, but we're not quite there yet.
Yeah, I was just thinking about the interpretability discussion and the continuous development.
Well, and I guess that puts an interesting spin on it, because if your notion of interpretability is that, well, if you have a PhD in physics, you can look at this and it kind of makes sense. Is that interpretable? I guess so.
At least for someone.
Yeah, at least for someone. Yeah.
So you said earlier that you eliminated part of the space that just burned through the sets or something. So with a huge range of time and energy, did you eliminate a combination of the two, or did you eliminate?
I believe it was a combination of the two. I don't remember exactly because, well, as I said, I actually didn't do any of this work. I'm just claiming the credit for it. But there was definitely some evolution process of the parameter space where we ran some experiments and then found, well, this is not worth it. And then cut it down to be able to eliminate stuff like this, but also then do the optimization more efficiently, because you don't need to look in those parts where we obviously know that nothing is going to be there. So kind of, you know, it's actually the opposite of what Holger Holz is preaching, because he's always like, well, once you have these automated methods, you can open up your parameter space and do more. And here's exactly the opposite. We have these automated methods and we're doing less because, well, we found that it just wasn't worth it. Don't tell him that I said that.
Yeah, no, it's not Jay. I'm thinking. I will send him the video link.
Excellent. Yeah.
Were you able to transfer at least some of the observations that were sensible then, though?
Transfer in what way?
Meaning you cut down your parameter space, and you probably, I mean, the obvious thing would have been that you might have found some configurations in that parameter space that were sensible, then you could immediately forward them in the next experiment if they asked the valid parameters.
Yeah, so we this is also something I want to look into. We haven't done this so far because essentially the differences between different batches of the material are large enough that this doesn't work. At least not if you just take the configuration and apply it there. Now, yeah, and it again, unfortunately, it comes down to they're really reluctant to just run stuff for the sake of finding out how the optimization works. But there's one of the things I want to do, right? So, you know, in particular, you could do the obvious thing of you just use your previous best results to seed instead of the initial random configurations and see if that's better. But of course, for that, you also need to run all of this multiple times, right? Because one BO run is not going to really tell you whether something is better or not. And suddenly we're talking about months and months of their students spending time producing material that is not going to get them anywhere. So, yeah, it's a bit difficult, unfortunately. But yeah, lots of things to explore there. Okay, so what's going on here? There we go. So here's some pictures that show you what actually happened. So on this side here, we have one of the relatively bad parameter configurations. You can see this massive meteorite-like, this is magnified obviously. You can see this massive meteorite-like holes are really not very good at all. And then on the right-hand side, one of the optimized configurations, much neater. In particular, the gray is kind of funky here, but this is supposed to be more silvery, which is, you can also just look at these, and you saw it on the sample going around. Some of the points are more silver than others, and that essentially denotes very roughly that they were converted to graphene better. So this is what we were going for here. Here, same thing as before, except with a much smaller number of iterations, so just to show you that we can do this with a much smaller number of iterations as well. So here we started with, here we did a total of 19 evaluations, including the initial random ones. And here the results are actually even better, right? Because if you look at the box plots, random and VO, they don't overlap at all. So here we got much better results, much better improvements than on the previous slide. But of course, this is not what happens in every case, as I mentioned. There was at least one case where during the random evaluation we found the best point, and we were never able to improve on it, but hey, yeah, that's life. So yes, and the code for this can be used by domain experts in chemical engineering that have no background in AI and machine learning. And I know that because I gave them the code and they were able to use it. At least they gave me results back, so I assume that it worked. And they made this cool video of the automated setup that you saw at the beginning. Yes, okay, so some more results here. What you saw before was graphene oxide as a precursor material on quartz, and these were the monochromatic samples that were going around. This is graphene oxide on Kapton. This was this orangey plastic that you saw in the samples that were passed around. Point is, it also works for different precursor materials, so it's not specific to, obviously, because we're using Bayesian optimization in other contexts as well, but it also works if we apply this to different kinds of precursor materials, and we can also do this directly on Kapton, so just the orange plastic that you saw. Here the results are not as good, so this is one of the cases where one of the points we found, one of the evaluations we did during the initial random sampling was actually the best one, and we were never able to improve on it. So results vary, but the methodology certainly applies, unsurprisingly, to all of these different cases, and we do see some improvements as well for these different cases. Yes, okay, so the other thing I mentioned, and the stuff that's more recent, is where we eventually want to go is we want to produce lines, right? Because this is what we need for circuits and sensors and stuff like that. And what we're really interested in optimizing, instead of this ratio, which is kind of a proxy for resistance, is the electrical resistance. As I mentioned before, this makes things much more difficult because we can't measure that in situ. So we have to take the sample out of there's actually a human that has to take it out of the reaction chamber, and then put silver ink pads at the end of the lines, and then put a probe there to measure the resistance. For the optimization that we're doing, that means that we can no longer do this individual point evaluation where we evaluate something, we measure the result, we update our surrogate model, and we propose the next point, but instead we need to go to batch evaluation where we need to I think it was around 10 lines that we can do on one of these samples, where we need to propose essentially 10 points in the parameter space, then evaluate these, then we get the measurements back, and we can update our surrogate model and go to the next iteration here. So this is what we did here, and we used the very simple strategy of constant liar for the batch optimization here, and that worked reasonably well as well. So here now we're minimizing because we're interested in resistance, so lower is better. Again, the initial random evaluations, and then we have the box plots here for the individual batches that we did. Not quite as good, so this is still work that is somewhat in progress. You can see that at least some of the batches, as we kind of, if you fit a line to this, it would roughly go down, so at least we're going in the right direction here. But overall, for the Bayesian optimization, we're not doing very differently, really, to the initial random point, but you can see that at least it looks like we're going in the right direction here. Okay, so I'm going to slowly wrap up here. It looks like we'll have plenty of time for questions. Just to give you a feeling for this, this is very roughly the code that we use for this. So this is this is our code based on MLR, MBO, and so far we've really mostly been using the library as is. So we haven't had to implement any custom things, and we haven't had to do any extensive modifications. And then it's essentially as easy as this. You define your parameter space, so here for the 3 parameters instead of the 4. And we set up the Bayesian optimization, we read in our data, we initialize our Bayesian optimization, so that trains the surrogate model, and then we propose the next point. And this is actually what's at the core of the code that the domain scientists were using. Particularly, it was really this, that they are working on this with a CSV. So at least to start with, when we didn't have the fully automated setup, it was essentially somebody sitting there, running the experiment manually, updating a spreadsheet, and running this code which reads in the spreadsheet and then spits out the next point for you to evaluate. And now this is fully automated, which was mostly difficult because interfacing with all these different machines is kind of messy, so they all have proprietary protocols, are, if you're really lucky, documented, and then they do weird things that are not documented, of course. So that took some time to get working as well. And of course, if you're doing things like the batch proposals, that becomes slightly different, but relatively straightforward code to do something relatively sophisticated, in this case here, largely leveraging really ML or MBO and those implementations there. Okay, so what other things might we do with this? What are we thinking about? Application of other materials. As you've seen, there's different ways to get graphene, essentially, for different precursor materials, and we might apply this to other ones. Then, as I've kind of said several times already, a more in-depth investigation of what Bayesian optimization does and how we might be able to improve it, in particular with respect to the exploration-exploitation trade-off, right? So this is the obvious one. But then also possibly other approaches, like should it be Bayesian optimization, or should it maybe be something else, like a much simpler stochastic local search, or some reinforcement learning, or something along those lines. Then, and I hinted at that already as well, a combination with additional layers of evaluation. So for example, computational simulation, so density functional theory, which will lead us into this area of multi-fidelity, if you want to call it that, optimization, or hierarchies of evaluation, which actually also becomes important in another context, because for the batch optimization that I mentioned earlier, what we can do in situ is measure this ratio of the peaks in the spectra, as I've said before. So we have these two different methods of evaluation, where measuring resistance is really what we're actually interested in, so this is kind of the gold standard. But then we have the spectrum that is kind of a proxy for this. We're still investigating that, which we can measure in situ. So we could kind of have a multi-fidelity batch optimization, where we can update part of the surrogate model or one surrogate model during the batch evaluation, measuring this ratio of the peaks in the spectra. And then afterwards we get this additional information for measuring the actual resistance of the lines. That's also something that we started to think about. So lots of things we started to think about, but we still need to make some progress there. And really, in the end, one of the things we want to do, or one of the things I want to do, is develop this into a general framework for this kind of optimization in material science. Because Bayesian optimization is used all over the place. In many cases, unfortunately, people have their custom implementation of Bayesian optimization. And like, really? And the other thing that makes me hopeful is that for the first paper here, we made the code and data available, and this was actually picked up by a completely different group, which used it for their completely different method of producing graphene, and also got very good results there. And we only saw that after they published a paper and cited us and said, hey, yeah, we're using their code. Like, whoa, what? Excellent. Yeah.
What is needed? What surrogate model-based optimization like MLBO, like SMAC and so on is not offering right now? Is that the connection to the sensors or to the lasers, or what is missing? What we don't have right now in our...
For this last point.
For the last point. What is missing for a general framework?
I think it's mostly documentation. And in particular, providing examples.
Okay, we are working on that.
Because, fantastic. But all the pieces are essentially there. It's just that people that might want to apply it are not aware of it. And then they're like, well, okay, hang on, this has been applied to AutoML. Wait, that's completely different to what I want to do, so I'm going to do my own thing, kind of. Whereas, like here, if there's an example, yeah, this has been applied to graphene production. Oh, okay, that's similar to what I'm doing. Maybe I can just apply their code there. But then also, in particular, if you're coming at this not as a computer scientist, you have a completely different perspective on it. Because I showed you the code earlier, right? And said it's easy to understand. Who agrees with me? See, that's the first problem. So, but me looking at something and saying, yeah, that's completely straightforward, I know how to do this, is not the same, obviously, as even students of automated machine learning looking at this and saying, yeah, that's obvious, I know how to do this. Never mind somebody in chemical engineering, for example, or in physics, who's kind of, coding on the side, but never had any formal instruction in programming. And certainly not R and stuff like that, looking at this and be like, I don't know, I can't even decipher this error message that I got here. I can't even figure out how to install this thing. What do I need to install for this? That kind of thing. So, and then in addition to that, it's really more sophisticated approaches in terms of modeling. So that you, for example, have like a Gaussian process that can take multiple levels of fidelity into account directly. Well, to some extent, it's what you mentioned, interfacing with all the machinery. I'm somewhat skeptical on this simply because we can't do this exhaustively, right? And we certainly then can't maintain all of this stuff. And really because in many cases you actually need the experiment, the physical machine in many cases. So if we don't have it, we can't do it. But this is where we hope to build up a community around this, and that might take care of some of this. But yeah, I think the main thing is really just documentation and kind of making people aware that this exists, and you don't have to implement your own Bayesian optimization, which, like I said, a lot of people really do. Yeah.
You mentioned that on the spectrum in the multi-fidelity slide that the chemical engineering department was working on simulators for this. Is there any idea on how accurately can this process be potentially simulated so that we could get some more, evaluations there?
I have no idea. So that this is where they brought in more collaborators from other departments as well, and that's a difficult problem in itself. So just being able to simulate parts of this process with any kind of accuracy is probably going to be a really prominent paper in the domain literature already. So yeah, we've started working on this, but I have no idea whether this is something that we can usefully integrate into this process.
So you don't have any kind of surrogate benchmark or?
No.
Okay.
I created
Too bad,
one.
because I would like to compare against Mac.
Yeah, so I created one, and you can find this on, I don't think I have the GitHub link in here, but it's referenced at least in this second paper here. So I put all the data that we gathered in all of these experiments, plus more of the R code that you saw in a GitHub repository. And this also, one of the ways in which you can use this is that it uses the data to build a surrogate model, which you can then optimize on. So, the common way of setting this up. I don't know how useful this is going to be because, like I said, I don't think that for the surrogate models that we build, we really have a very good we don't have a comprehensive view of the landscape. Some parts are well explored, some tiny parts, other parts we don't know anything about these. But if you want to do that, if you want to try SMAC on that, you can. Well, you would need to integrate with my R code, so that's obviously going to be very straightforward and easy.
We have 2 more days?
Yes, but no, I can definitely point you to this. Any more? Yes.
I actually wanted to ask, and maybe you might have already answered that, but how do you plan on resolving the hierarchy of fidelities? Because you kind of have, might have, for instance, the thing that the actual experimentation informs the higher fidelity. Sorry, the actual vicarious fidelity, so the simulation.
Right.
And then you kind of have to fuse the information of it.
Yeah, so we haven't really started to think about this because we don't have these layers yet, right? Well, okay, so the only thing that we have is what I've briefly mentioned here, where we now have this batch optimization, where after 10 lines or something like that, we can measure we can take a second type of measurement that we can then feed into the process. So you started thinking a little bit about this, but that essentially, I mean, at least our preliminary thoughts on this are that you probably just want to do 2 different surrogate models and then you combine their predictions. That at least would be the straightforward way of doing this. And it's not immediately clear that combining them would give you an advantage because essentially the 2, I have to go off on a completely separate thing. The 2 measures are meant to be proxies of each other. So the ratio that we measure of the peaks in the spectrum are supposed to be a proxy for the connectivity of the lines, or the resistance of the line, which we measure. At the moment, it looks like this might not always be the case. So there's some other stuff going on there, which we haven't entirely figured out yet. So like I said, these results are like a month old or a little bit more than that. So we're still working on that, but essentially things were not quite as we have expected so far, and this is what we need to investigate more. And this will then also determine to what extent and how we might want to integrate that. Or maybe we will just say that, well, you know, measuring the spectrum and the ratio between the area and the peaks was good while it was the only thing we could do, but now we're going to throw it away because we have something better, and we have shown that it is actually better, and that it's not just one is not just a proxy for the other. Right. So, and that is actually the end of my talk. So yeah, acknowledgement of our funding agencies. Brief summary here. I'm happy to take more questions. I have a couple of backup slides for more technical questions that you may have. So yes, and I think we have about, what, another 10-15 minutes? Yeah.
Actually, I have a related question to the one earlier, where the entire process of the production is taken into place, into consideration. So you have a multi-step procedure that actually results in your probe. So
Yes.
do you take into account the measurements along the way regarding the batch that you receive to kind of inform your model? Because then you kind of could potentially transfer knowledge between multiple VO runs.
So wait, I didn't quite get this. What information do you want to take into account for this?
I want to take into account the kind of meta information about the batch that you get.
The meta information about the batch.
Which is kind of the what kind of parameterization or what kind of intermediate measurements resulted into this particular batch, because it kind of these intermediate measurements could kind of describe the structure of the batch that you receive before you actually probe your laser on it, and this could kind of inform your VO in a way, kind of what function you are looking at. So
we're not really taking any intermediate measurements as such. We run a batch, so we do a bunch of random evaluations to start with. Then to initialize our model, then we use constant liar to propose a batch to evaluate. And then we take out the batch, we measure the resistance of all the lines, take these 10 results or whatever, and use that to update the surrogate model, and then repeat that process.
Yeah, no, I mean in the production process of the batch itself. So how the material that you receive before you actually probe it is kind of...
yes, so this is something that we want to look at as well, because in particular, the number of times you spray the precursor, the carrier material, you control the thickness. This is something that we've been wanting to into account as well, except that it hasn't happened yet for various reasons. So because then, now you need to produce a bunch of batches with different thicknesses, and you need to be able to measure that, which is also not entirely straightforward. We could just do a number of passes, but yeah, so also something we're thinking about, but we haven't really done that yet.
Yeah, because I really think that if you were capable of doing that, I mean, yes, it is kind of a more complex space because you have more measurements to account for, so a more complex function in that space. But if you could kind of condition on the settings that created your batch, that should kind of improve your understanding of it.
Yes, but it does turn out that the person preparing the batch also has a large impact. And I don't know what exactly it is, but if it's somebody who has done this 100 times before, you get a much more consistent, much better quality batch overall, and you see much better results with the optimization. And if somebody is doing it for the first time, random stuff happens. Yeah. So there's definitely more to it. But yeah, so we have thought about essentially putting more context into this evaluation, for example, through the thickness. But that has also really, again, just the expense of producing material. This is where it kind of falls down at the moment. And maybe eventually we will get there, but it might take another couple of years.
How impactful is the human error that you just mentioned about, like, for example, if you were to get more information about it, more context into it, right? You said that there could be human error in terms of how impactful is that in your experience so far in the process?
Well, I can't really answer that question because I'm not preparing the batches or running the experiment. From what I've heard, it tends to have quite a large impact. So for example, like I said, the person preparing the batch tends to have a large impact. Now, how does that relate to, oh, let me put it this way, as far as I know, it's not so large that that might be the source of the improvements that we've been seeing. So it's not quite as large, but it's an additional source of noise essentially.
It just adds more noise to it.
And this is something that we also can't really model, right?
Yeah.
Apart from, oh yeah, it was person A. Oh no, wait, it was person A on Monday versus person A on Friday, right? So it's just, it becomes really difficult. Yeah.
So you say that a different person might prepare the batches during one optimization process. Does that mean that the noise is heterogeneous?
There is what, sorry?
The noise is heterogeneous, so that the noise in different area is different. Like,
Potentially yes. We haven't really measured this yet, but so what really the only noise measurements that we have done is for one particular batch, you run the same configuration multiple times, how different are the values that you measure.
Yeah.
We haven't really investigated this, at least not in principal fashion, across batches. We've essentially said that, well, all these experiments, these results are specific to one batch. So like these experimental campaigns that we saw, you saw, they were all run on material from the same batch because we know that there are differences between different batches and we haven't quantified those yet.
So at the Gaussian process, it's very hard for Gaussian process to model these noises, this sort of noises. So we assume that all
well,
noises are the same in Gaussian.
I'm not even sure if the noise would be Gaussian necessarily. It could certainly be. It would be something to have a look at. We haven't had a look at that yet. But yes, there are unfortunately many sources of noise. At least we've eliminated one by completely automating the experimental setup. So we don't have to have the human there because, I think in some of the early days it also just, the usual human thing. After you've been doing this for 8 hours and writing down numbers, you accidentally copy one number somewhere and stuff like that. So it just happens, right? At least that's not an issue anymore because you have automated this. And now it's really, essentially you press a button and then you go home and you come back on Monday or something and there's your finished experimental evaluation. More questions? Yes?
If you would like to minimize also a different parameter, add it to the resistance, how would this change the whole experiments and also the process that you selected?
So is the question what would happen if I swapped out resistance for another measurement or if I added something to?
If you add, for example, you say, okay, I don't want to set the maximum power on the laser, I just need a small laser power because
I see.
Know,
okay.
because it's too expensive.
Yeah, so that then would essentially be, well, let me go back to the code here. That would essentially be an adjustment of the parameter space. And you can,
okay.
I should emphasize, we haven't done this, but you can also specify dependencies and like weird things in your parameter space. So we could also encode that essentially we don't want combinations where we have large power and high duration, but large power and low duration is fine. So as in we don't want to adjust the upper value for power, but we want to essentially say that you shouldn't choose the upper value for power and time at the same time. And so far we have simply opted to essentially let the spatial optimization learn this, right? We're trying something and then seeing that, oh yeah, okay, if I go in this direction I see bad results, let's try going in the other direction. Yes?
So how expensive are these calculations, so to say? Is it
This here?
Milliseconds or?
Probably not milliseconds, in particular because it's integrated, but it's a holy mess of Python and R and possibly other languages. So I think the whole thing is driven by an IPython notebook, which then calls out to R code and stuff like this. So just because of that, there's a little bit of overhead. I think it's in the order of seconds, at least for the amount of data that we're working with, which is dozens of data points. Of course, as you get more data points, this might take longer, but it's certainly, the actual evaluation takes way, way longer. So that's not the bottleneck here, and that's all we care about at this point. Any other questions? 1.5 hours must be up. Almost. All right, well, then, thank you very much.
Thank you very much.